Welcome to The Explainer. Today we're tackling one of chemistry's greatest stories, a real head-scratcher about a molecule that hid its true identity for more than 100 years. It's a tale that features a famous daydream, a snake, and a huge leap forward in how we even think about the stuff that makes up our world.
So, let's start with this quote. It's from the chemist Friedrich Kekulé, and it describes this famous dream he had. He's dozing by the fire, imagining atoms, when he sees a snake bite its own tail. And just like that, it clicked. Maybe the atoms formed a closed ring. You have to remember, at the time, this was a wild idea. Everyone thought carbon molecules were just straight chains.
But here's the thing. That brilliant flash of insight, it didn't actually solve the whole mystery. In fact, you could say it created a brand new puzzle, one that was even trickier, and would take another 65 years to fully figure out.
And this timeline really puts into perspective just how long this puzzle was on the table. It starts way back in 1825 with Michael Faraday discovering the stuff. 40 years go by, then Kekulé has his dream about the ring, but then another 65 years pass before our technology, specifically X-ray crystallography, gets good enough to actually see the molecule. And that picture, it just opened up a whole new can of worms.
So, here it is. This is the heart of the whole mystery. Kekulé's drawing with its alternating single and double bonds pretty clearly suggests that you should have two different bond lengths in the ring, a short one, then a long one, then a short one. But when scientists measured them, they found something incredible. All 6 of the bonds were exactly the same length. They weren't single and they weren't double. They were something in between. How is that even possible?
All right, so to crack this nut, scientists reached for the best tool they had at the time for explaining chemical bonds, valence bond theory. It's a great theory, it really is, but for this particular problem, they were about to find out it just wasn't enough.
You know, the idea behind valence bond theory is actually super intuitive. All it really says is that a bond happens when the electron clouds, the orbitals, of 2 different atoms overlap. It's kind of like they're sharing that space and the electrons in it. Think of it as 2 atoms deciding to hold hands.
And for something really simple like a hydrogen molecule, this theory just works. It's beautiful. You take 2 hydrogen atoms, they each have their little spherical s orbital with 1 electron. Those orbitals overlap. The electrons pair up, and bam, you've got a stable H2 molecule. Simple, elegant, perfect.
Okay, simple stuff. Check. But then you get to a molecule like methane. That's 1 carbon with 4 hydrogens, and suddenly this straightforward model just hits a brick wall. This is where it all starts to get a little bit weird.
See, if you just look at a standard carbon atom's orbitals, the theory predicts that methane should have 2 different kinds of bonds holding it together. But when you look at an actual methane molecule, that's not what you find. Not at all. All 4 of its bonds are absolutely 100% identical. The theory just didn't match reality.
And this is where the story gets really cool. This failure, this problem with methane, forced chemists to come up with a totally new and absolutely brilliant idea that would change everything. Orbital hybridization. It's the secret sauce that lets atoms build these perfect, symmetrical shapes.
So, what is hybridization? Well, imagine you have 1 can of red paint and 3 cans of yellow paint. If you need 4 identical cans of a perfect orange, you're not going to use them separately, right? You're going to mix them all together first. Atoms basically do that with their orbitals. They average them out to create a new set of identical hybrid orbitals that are just right for bonding.
So, for carbon, here's how it pulls this off. First, it nudges one of its electrons up an energy level so it has 4 unpaired electrons ready to go. Then it does that mixing trick we just talked about. It blends its 1 s orbital and its 3 p orbitals. And what comes out? 4 brand new, perfectly identical hybrid orbitals, which we call sp3 orbitals. And guess what? They point to the corners of a tetrahedron, perfectly explaining why methane looks the way it does.
And this isn't just some one-trick pony for methane. No, hybridization is like a whole toolkit for building molecules. As you can see, you can mix the orbitals in different ways to get different shapes. Mix 1s and 1p, you get a straight line. Mix 1s and 2p's, you get a flat triangle. The type of hybridization basically dictates the final shape of the molecule.
Okay, so now that we've got this new tool, hybridization, in our back pocket, we can finally go back to our original villain, benzene. But to actually solve the puzzle of the ring, there's one last detail we need to understand, and that is not all bonds are made the same way.
It turns out there are two main flavors of these bonds. First, you have sigma bonds. These are your workhorses. They form from a direct, head-on overlap of orbitals, and they are super strong. Every single bond is a sigma bond. But if you want a double or a triple bond, you need to add another type, pi bonds. These are formed by a weaker, side-to-side overlap.
So here's a super important rule of thumb. Whenever you see a double bond drawn between two atoms, what you're really looking at is one of those strong sigma bonds with one of those weaker pi bonds layered on top.
And you can probably guess what's next. For a triple bond, it's the same idea, just more of it. You've got that one strong sigma bond holding things together at the core, but this time with two pi bonds added on.
Okay, deep breath. This is it. We're putting all the pieces together now. In benzene, each of those 6 carbon atoms uses sp2 hybridization. Remember that one? It's the one that makes a flat triangle. This creates the flat ring of strong sigma bonds that holds the carbon atoms together. But sp2 hybridization leaves one p orbital on each carbon totally untouched, just standing there, sticking straight up and down, perpendicular to the ring.
And this is the punchline. This is the solution to the whole puzzle. You've got 6 of those leftover p orbitals, one on each carbon, all lined up in a perfect circle. And their electrons? They don't bother pairing up into 3 separate double bonds like Kekulé thought. No, instead, they all merge together. They form one continuous, unbroken cloud of electrons, like 2 donuts, one above and one below the entire ring. The electrons are delocalized.
That cloud, that continuous ring of 6 shared pi electrons, that's the answer. Because those electrons are being shared equally among all 6 carbon atoms at the same time, it makes every single carbon-carbon bond identical, a perfect hybrid between a single and a double bond. Kekulé's snake finally makes sense. It wasn't biting its own tail. It was part of a continuous, unbroken circle of energy.
So the story of benzene, it really shows us that those simple lines we draw in chemistry class, they're just a model. They're a useful cartoon for a reality that is so much weirder and, frankly, so much more amazing. Bonds aren't just sticks. They're these dynamic, shimmering clouds of probability. And it just makes you wonder, what other incredible secrets are still waiting for us, hidden in the quantum world of molecules?